Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
The biotechnical synchronization is complete. Semiconductors show seamless integration. Alloys bond with the tissue interface. Quantum dots track real-time cellulability is achieved.
The body has 4 primary tissues. They are epithelial, connective, muscular, and nervous. Epithelial tissues line boundaries and form structures. Nervous tissue originates from the neural plate.
Nerves are protected by 3 layers. The epineurium wraps the entire nerve trunk, the perineurium surrounds individual fascicles, and the endoneurium insulates axons. They dictate physical susceptibility. Some tissues lack regenerative capacity. The brain is highly vulnerable. Protected, it experiences low shear. Living fascia behaves as a dynamic liquid crystalline matrix. It is composed of closely packed collagen fibers, hollow, fluid-filled protein nanotubes. Consequently, these collagen structures attract water molecules, organizing them into a highly structured, liquid crystal layer. This network generates electrical charges, enabling smooth glide between muscular structures.
Trauma triggers a gel-to-soul transition. Fascia hardens, exerting extreme pressure. This restricts microvascular blood flow. It compresses adjacent peripheral nerves. This
Physiological communication relies on 2 integrated signaling systems, the fast nerve impulse and the body-wide tissue matrix. This relies on voltage-gated sodium and potassium channels. This electrochemical process is limited by synaptic delays. In contrast, the fascial matrix acts as a bioelectric conductor. This allows rapid transmission of signals throughout the body.
Because the collagen fibers naturally orient themselves along lines of physical stress, these bioelectric currents propagate directionally, enabling real-time coordinal structural systems.
Axonal conduction relies on gated channels, creating a slow, measurable synaptic delay. But fascia uses structured water, enabling rapid, near-instant proton hopping. The neural ECM actively regulates conduction. It forms diffuse matrices and dense networks, regulate receptor mobility. Perineuronal nets wrap fast-spiking interneurons. Resting microglia migrate to the site of injury and transform into an active, pro-inflammatory phenotype. Reactive astrocytes are activated and accumulate to form a dense glial scar. This glial encapsulation acts as an electrical and physical barrier. It physically isolates the active electrode sites from nearby neurons. This degrades the signal and limits long-term functionality.
Precise synchronization at the biointerface is critical. Lithium ions compete to modulate vital pathways. This advanced integration defines the future of medicine.
Silicon nanomembranes feature a diamond cubic structure, designed to dissolve safely through hydrolysis after monitoring, while silicon carbide forms ultra-stable neural rigid trigger glial scarring due to mechanical mismatch. Germanium powers next-gen transient biosensors. These passivated barriers prevent direct corrosion, a massive breakthrough for clinical biotherapeses. Chromium forms a face-centered cubic matrix, used in joint replacements and stents. An oxide barrier resists corrosion, but wear can release toxic ions, causing necrosis. Lithium was excluded from early complex life. It competes with magnesium at critical enzyme sites.
To improve lithium therapy, researchers are using advanced DFT calculations. They analyzed hollow nanocages alkali metal ions. This low-dose delivery vectors into human cells.
Bader charge analysis indicates that when lithium is incorporated, the negative charge of the oxygen atoms in the nanocage increases, promoting the transfer of monovalent ions. This narrow HOMO-LUMO gap increases electrical conductivity. It boosts ion transfer efficiency across the lipid therapeutic ions, directly targeting neural sites, reducing toxicity. Cobalt-chromium alloys are ideal for medical implants.
They provide high strength and wear resistance. Used in hip, knee, and dental restorations, they ensure long-term reliability.
These alloys rely on a passive layer, but stress breaches this barrier, triggering continuous tribocorrosion, releases toxic wear debris and ions, leading to tissue bone loss and system toxicity. Joint implants are subjected to continuous wear. This leads to tribocorrosion at modular junctions. Fretting and crevice corrosion breach the protective layer. This releases debris and metal into surrounding tissues. Free metal ions bind with anonic proteins. This activates the cellular immune system. This triggers macrophage and necrosis. This microenvironment asymmetrical osteolysis and aseptic loosening. This excessive posterior slope creates flexion gap instability. The polyethylene bearing wears through rapidly, resulting in metal-on-metal wear and debris release.
Bioresorbable electronics operate stably in vivo and then dissolve completely into non-toxic byproducts, utilizing ultra-thin silicon nanomembranes. Silicon nanomembranes undergo chemical dissolution via hydrolysis. This yields orthosilicic acid, safely excreted by the kidneys. Polymers like PLGA.
Conventional neural probes often fail chronically. Monolithic silicon carbide withstands the environment.
Crystalline silicon carbide offers a robust, monolithic alternative. Failures. Support is micromachined from P-type size. Isolation is achieved through a PN junction.
This design restricts leakage currents to less than 1 nanoampere under 50 volts. Amorphous silicon carbide prevents shorting.
These monolithic SiC devices are highly compatible with MRI. 3C SiC films show no observable image artifacts 7 Tesla. Modeling predicts a 30% reduction in SAR, minimizing localized heating.
Germanium offers higher mobility than silicon, but its native oxide is highly water-soluble, and it thermally decomposes at high temperatures.
To prevent degradation, thin films are utilized. These are deposited via PECVD at low temperatures. They act as reliable passivation layers. This controls dissolution kinetics.
Integrating nitrogen into the lattice forms a GeoX-NY film. This raises the thermal stable phases suppress outdiffusion and act as effective barriers. In MIS structures, surface dangling bonds are passivated. This minimizes trap density and reduces leakage currents. This enables the stable operation of transient biosensors.
Inserting rigid arrays into the brain is a major challenge. This mismatch drives the chronic foreign body response. This leads to a decline in performance.
To minimize mismatch, these arrays utilize amorphous silicon carbide. This significantly reduces their flexural rigidity, minimizing micromotion, 40-fold reduction compared to conventional probes. This simulation charts insertion. At the tissue interface, compression builds. Axial penetration ensures successful localization. Without rigid support, buckling occurs, resulting in implantation failure.
Highly flexible probes can buckle during insertion. The critical force must be at least twice the penetration force. This formula ensures a successful implantation.
Biomechanical studies demonstrate probes with a ratio of FP to FC consistently achieve a 100% success rate for unaided insertion into cortical tissues. To optimize these dynamics, tapered probe geometries and vibration-assisted insertion techniques are utilized. Planar ASIC probes with a tapered profile exhibit lower peak penetration forces. Co-fabricating the probe allows for high-frequency vibration. This actuation reduces friction and pile dimpling. 40% of insertions show no peak, penetrating parenchyma with minimal resistance.
Once implanted, the mechanical stability of the probe is maintained by biological force. Under physical stress, the protein piezo-1 triggers production of molecules such as semaphorin 3A.
Piezo-1 modulates cell adhesion proteins, including NCAM1 and N-cadherin, essential for maintaining stable cell-to-cell contacts. This promotes integration and improves recording stability. From clinical to experimental, BCIs are transitioning to advanced monolithic structures for long-term signal stability. Bioresorbable pacemakers control heart rate during recovery. They are fabricated from silicon nanomembranes and biodegradable metals. These devices dissolve completely into non-toxic byproducts.
These epidermal trackers establish conformal contact with the skin. They integrate flexible silicon ribbons onto elastomer substrates. This allows for high fidelity of vital signs. These bioresorbable arrays monitor deep organs. Backward-facing barbs ensure stable anchoring. Tips continuously monitor pH and oxygen. Then, they safely degrade into the body.
High-load joints utilize cobalt-chromium alloys. They also provide strength for coronary stents. Protective coatings prevent ion release, suppressing inflammatory effects in the vessel.
High-bandwidth neural data generates dangerous heat. To resolve this, researchers developed a neuromorphic chip. This chip transmits data only when a change in activity occurs.
By grouping correlated events, the NCT chip reduces data volumes by more than 10-fold. Operating at an ultra-low power of 0 microwatts, it ensures safe clinical implantation.
Germanium oxides are inherently unstable. Wet chemical treatments create robust, inert linkages. This passivates the surface against reoxidation, enabling stable, highly sensitive biosensors.
Integrating advanced semiconductors is a major shift. Manning properties. These architectures minimize mechanical mismatch, enabling long-term recording stability.
Bioresorbable silicon membranes allow for temporary high-performance implants that dissolve completely to improve clinical outcomes, expanding our understanding of human physiology.
Like what you share.
This website makes learning so easy. I found all my resources here.